essentially says that the world, the commitment here is not about degree of belief, but degree of truth. That means a particular statement. When I say 4 by 7 probability, that means in 4 words it's likely to be true, in the other 3 words it's likely to be false. Fuzzy logic says in a given word, this statement is 0.7 true. In a single given word, the statement is 0.7 true, which is a different kind of commitment. These, the probabilistic logic and fuzzy logic are very different beasts, actually. Okay, we will mostly not talk about fuzzy logic. There are all sorts of interesting problems that come up if you actually try to do fuzzy logic because it tries to use degree of truth and uses more or less the rules of propositional logic, and that leads to all sorts of inconsistencies. But people do use it and get some results, but theoretically it's not of a sound basis. Okay, this is more or less what your textbook would also say. So that's your fuzzy logic, and then these are all the holy sorts of logics, and of which I would definitely do this, I definitely do this, and then do the others depending on it. Okay. Now, before I go forward, I want to say, remember I said all logics are defined in terms of words, and a fact may be either true or false in a word. Think in terms of propositional logic. Think in terms of John and Mary came to the party kind of situation. So the question then is the notion of, you would say a word where a fact F is true is called a model of F. That means it's a word where that fact is true. So if you make a fact which has no models whatsoever, that means there doesn't exist a single word where this fact will be true. Can you guys, at this level of abstraction, can you guys give me a sentence in the John Mary going to party format which has no models? Do you think, first of all, if I say John and Mary came to the party, you can imagine there being a word where both John and Mary came to the party. So it's satisfiable. John or Mary came to the party. You can imagine a word where either one or two, either one or the other or both have come. That's also fine. Yes?
Would John came to the party and John didn't come to the party be one?
There you go. John came to the party and John didn't come to the party. You see what I'm saying? So these are called unsatisfiable sentences. They have no models. You think, what is the point of thinking about these sentences? Why think of sentences for which there is no real world, there is no formal word where that sentence can evaluate to true? Just hold on to that thought. We'll find out that unsatisfiability is a bedrock of logics. In fact, you convert the question of does a fact follow from what I know to showing that the knowledge and negation of this fact is unsatisfying. Do you understand what I'm saying? Think about this. John and Mary came to the party is a sentence. And you all agreed that that implies that Mary came to the party. That means Mary came to the party is entailed by the knowledge John and Mary came to the party. How do you know? Here is a way. Take what you know, which is John and Mary came to the party, add to that the negation of what you want to prove. You want to prove that Mary did come to the party, so you add Mary didn't come to the party. So now I have this complex sentence saying John and Mary came to the party and Mary didn't come to the party. That's just a complex version of the thing that he was talking about, because it has as part of it, Mary came to the party, Mary didn't come to the party. It's unsatisfiable. So in fact, you prove things by showing that the thing that you want to prove, if it's not true, with respect to what you know, then, I mean, if you take what you're trying to prove and negate it and add it to what you know, there can't be any worlds where all of this will be true. By the way, there is a mathematical proof technique which actually uses it. What is it called? Exactly, proof by contradiction. You want to prove something, you take the negation of what you're trying to prove and say, no, that's not possible. There's no world where this is possible. When did we use this proof in this class?
A star.
A star search. All proofs are logic. Do you see what I'm saying? Okay, so all of this basically is getting you to the point that really, if I have a knowledge base, then there are some worlds in which the entire knowledge base holds. That means everything in the knowledge base is true in those worlds. Let's consider that set. Let's just say, here is the set of worlds where the knowledge base is true. Now I want to check if alpha follows from the knowledge base. That means, is it entailed? Can I, knowing KB, can I write alpha? Knowing Mary and Tom came to the party, can I write Mary came to the party? Right? So the question then is, well, everything, in fact, this is this particular set of worlds, set of models of KB is its meaning. When you think of what is the semantics in logic, the meaning of a sentence is the set of words where that sentence is true. See what I'm saying? Which sort of, when people are saying, my life has no meaning, I'm not quite sure what they're talking about. Okay, but here I know that in logical sentences, you say that a sentence's meaning is just the set of words where it is true. So John coming and John not coming at the same time to the party, that set is empty set. So it has no meaning. Okay? So here is the meaning of KB. Alpha itself is another set. But alpha basically, if I'm trying to write alpha as a sentence, then it has probably a set of words where it is true. So my question then is, let's see if I can do this. So I can consider the following thing. Suppose this is the set of words where alpha is true. Can I say that alpha can be written to be true because knowledge base is true? When I said knowledge base is true, that means I am in one of the worlds here. Do you understand what I'm saying? In fact, if I have, let's say, PQR as the propositions, then I said there are 2 power 3 or 8 words. If I say P is true, how many words am I possibly in? Only 4. This actually tells you knowledge is equal to constraint. Do people understand this? Knowing something more constrains how your world is. The more you know, the fewer configuration the world can actually have. If I didn't tell you anything other than there are PQR in your world, you are in one of 8 worlds. I said, well, P is true. You're only in 4 worlds. P and Q is true. You're only in 2 worlds now. P and Q is true and R is false. You're in 1 word. P is true and P is false. You are in no world. Do you see what I'm saying? So in fact, you can count the number of words, given a knowledge base, you can count the number of words that are consistent with it. And remember, sometime back when we were doing the A-star search, I said, set superset relations, we take them for granted, but mostly everything can be proved from set superset relations. Here is another one. Okay, so you said this. So by the way, for entailment, you use this funny notation. If I am like this, KB does not entail alpha. How about this? Okay? These are all the words where KB is true. These are all the words where alpha is true. In this case, is alpha entailed? Is alpha entailed? Okay. How many of you think alpha is entailed in that case? Hit yourself hard on the back of your head and say, never again say that. Okay? It's very important. Understand why it's actually turns out alpha is not entailed. But why? Because when KB is true, imagine KB is true because you are actually in this world. Is alpha true?
Not necessarily.
Do you understand what I'm saying? So to be able to say that alpha is entailed by KB, the set of models of alpha should be a superset of the set of models of the knowledge base. We just converted entailment into set theory. It's not, we didn't do something new today. That's how basically mathematics, the semantics of mathematics has been done. Okay, but many people fall for this, don't fall for this. In general, this is, this is actually staring at you. This is the correct answer, right? This is the models of KB, and this is the models of alpha. In this case, you can say KB entails alpha. You guys got this? It's extremely simple. Okay, this is what you're trying to do. In some sense, entailment is really counting up the model, basically enumerating all the models where your knowledge base is true, and checking if in each of those worlds alpha is true. Do you see what I'm saying? This is true for propositional logic, this is true for predicate logic, this is true for first order logic. Why don't we do it that way? Why waste time talking some more hours here? Because this is a brute force way. If there are 10,000 propositions, there are 2 power 10,000 words. And you're talking about enumerating all those 2 power 10,000 words. Do you understand what I'm saying? How about, look at that guy's question. Suppose there are 10,000 people who may or may not have come to the party. That means the configuration of the party is 2 power 10,000. There are 2 power 10,000 different parties that can be happening. He wants to know whether, is there a party where John came as well as John didn't come? Will you go through all 10,000, 2 power 10,000 models to check whether that statement is true in any of the models? No. If you stop without doing that much computation, you win. That's what logical inference is all about. Doing entailment efficiently is what logical inference is all about. This is the definition. This is the definition of entailment as limit h tends to 0, fx plus h minus fx by h is the definition of derivative. Just as you never use this really to do derivatives, this is the definition. This is the semantics of derivatives. But you basically do this, if you ever do things directly from this, then you would say, directly by looking at the models, you would say model theoretic computation of entailment. And then we talk about a cheaper way called proof theoretic computation of entailment. It's the kind of thing that you know where you say, if A and B are true, then you get to write A. If A implies B is true and A happened, then you get to write B. If A implies B is true and you know B did not happen, you get to write A did not happen. So this is what I said. Let's see. A implies B is true. B did not happen. You get to write A did not happen. How many people think this is actually made up rule? This is Python rule. This is a sound rule. This is correct. Right? If in fact A, when I see it here, there. So A implies B. And B is not true. If A were true, B will automatically become true. Because you can't stop You see what I'm saying? This is not some sort of a process. As soon as A is true, in every world where A is true, B will be true. That's what A implies B means. Okay? And so if B is not true, then A cannot have been, could not have been true. This is actually, it has a name. It's called modus tollens. Okay, and similarly the other ones that you looked at, A implies B is true, A is true, then B is true. This is called modus ponens. And then there is this other rule. Where do I write this other rule? I need to find some space here. I'll write this other rule here. A implies B is true, not A is true. I'm sorry, A implies B is true. Okay, no, that's not A. A implies B is true, and B is true, so A is true. This is Python tolerance. It's not a logical rule. Okay? A implies B is true, and if just because B is true doesn't mean A is true. There could also have been D implies B. And D is true, that's why B became true. You see what I'm saying? Okay? Anyway, but these kinds of rules is what you thought of as logic before. That's called proof theoretic inference. And all inferences are trying to compute entailment. They're all trying to compute this. Just as chain rule and all the other rules of derivatives that you use are all trying to compute this ultimately. How do you prove chain rule to be correct? You use this definition. How do you prove any of these rules to be correct? You use this definition. This is the main truth in logic, main semantics of logic. Okay? Good. Questions? Okay. So that's entailment, and proof methods has there is a model-based proof checking, and then application of inference rules. Those are the two things normally that happen. And I've sort of been using, and then when you have an inference, you can talk about, since remember, ultimately what you're trying to compute is this. This is the relation you're trying to compute, the model theoretic. And then you made up a bunch of rules like A implies B is true, A is true, B is true. The question then is this rule capturing everything this guy captures? Do you understand what I'm saying? So I can ask the following question. If this rule says a particular fact is entailed, is it really entailed? That's one part of the question. The other part of the question is, if this semantic says a particular fact is entailed, will this rule be able to say that? Those are two different aspects. And one is called soundness. The other is called completeness. You will say a rule is sound if whenever you apply the rule, you write a fact to be true, you can be sure that that fact is actually true according to the model theory. And a rule is called complete if anytime any fact can be derived, anytime any fact can be proved to be true from the model theory, this rule also will let you write it. Okay. By the way, the word that is used when you write this is you'd say A implies B and B allows you to derive. You notice that derived relation is different from entails relation. And derives is being used to compute the entailment relation. Okay? And the question, of course, is the derived relation really equal to the entailed relation? And it would be sound if everything that is derived is actually entailed. It is complete if everything that can be, that is actually entailed is derived. Now my question is modus ponens sound? When you say it's a reasonable rule for logic, you say it's a good rule, that means it's a sound rule. If you use that rule to write a fact, it's actually true, it's in fact entailed. The question is it complete? The other question is it complete? It turns out modus ponens by itself is not complete. If you just use modus ponens, you will write a bunch of facts that are entailed. But there are a bunch of other facts that are entailed that you won't be able to write. You see what I'm saying? So it turns out the same for modus tollens. It is essentially sound but not complete. And there is actually one rule. In fact, until you came to this class, you have not heard of a propositional rule of inference that is both sound and complete. Okay, give me a rule that is just complete. It may not be sound. Give me a rule that's complete. It may not be sound. Notice that I separated these things out. Can you give me a rule that's just complete, but may not be sound, but it's complete for sure? Ask me a question. Is a fact F entailed? I'll say yes. Ask me another question. F2 entailed? Yes. This is called yes ma'am rule. Everything, whatever you ask, I'll say yes, it's entailed. Do you realize that it's complete? Would it be sound? No, because you're saying it the same for everything. So it is actually possible to come up with vacuously complete rules. It's actually possible to come up with vacuously complete rules. Okay? But getting a rule that is both sound and complete is pretty hard. In fact, most of you probably haven't heard of them, even though this is well known. How many of you have done logic courses? Okay, so you know what I'm talking about. What's the rule for propositional inference rule that is both sound and complete? That means if you just keep using that rule, you will get everything that is entailed and nothing more. Resolution. You guys did this in your logic classes, and that's what we'll do again. Okay? And so we'll keep some suspense and figure, I'll tell you what resolution rule is a little later, but resolution rule of inference basically is a generalization of all these rules. And if you just keep using that rule all the time, then it's both sound and complete. By the way, this separation of soundness and completeness is connected to a bunch of other things. If you ever go to a court of law, they will make you take a pledge, right? They make you take a pledge before starting being a witness. What does the pledge go? Yes?
Tell the whole truth and nothing but the truth.
Okay, say it again. Whole truth and nothing but the truth. Why two parts? Is it just because of old English nonsense? You see what I'm saying? Whole truth is soundness. Nothing but the truth is completeness. I'm sorry, whole truth is completeness and nothing but the truth is soundness. Okay? There is another set of words that you know, some of you know, which is precision and recall. Same idea. Precision essentially is connected to soundness. Recall is connected to completeness. And complete and sound means precision 1, recall 1. Okay? Keep that in mind. Okay, so now we'll just walk through this very quickly because I'm assuming that you know logic. So this is sort of the syntax of logic. S1 implies S2 can be written this way or it can be written this way. How many of you have not seen logical notation like ever before? Those of you who better make sure that, in fact, I asked you to read the readings, that would have also made sure that you understood the logical notation. Okay, many of you have seen it multiple times in your life. Okay, so that's your propositional logic. This is a syntax. These are the kinds of things that you can write. So can you give me a sentence that's not even syntactically correct? Yeah.
One equals.
What?
One equals.
One equals. No, in fact, it turns out there is no equals yet. And equality is typically added on top of this. The simplest propositional logic only has this one called conjunction. This one is called disjunction. This one is called negation. And this is called implication. And in fact, it turns out A implies B is identically equal to not A or B. This is actually very important for people to understand. Many people look at A implies B and think it is a causation. A is causing B. No. It's just a fact about the worlds where A and B are found to be true. See what I'm saying? In any world where A is true, you can just close your eyes and say B is true too. In any world where B is not true, you can close your eyes and say A is definitely not true. In any world where B is true, you can't say anything about it. You see what I'm saying? Okay, so my original question was, can you give me something that's syntactically incorrect? Yes.
A and not A equals true.
No, none of them. So I'm just talking, it should be, syntactic correctness means compiler should say, are you on drugs? This program doesn't compile. What? What? A conjunction, yeah, so something like this. Like this. You see what I'm saying? These are all basically syntactically incorrect sentences. So those are the ones where basically you have a parser. The parser can't even parse the sentence. No, it's not syntactically. So I can write pretty darn complex sentences within this syntax, right? P and Q implies R, or J, R, M, and J, R, M are not K, implies W. This whole thing implies M, R, P. I wrote a huge long sentence. This sentence also, given a single word, it will either be true or false. Do you see what I'm saying? Just like this is basically syntax. Okay. Now the semantics is basically, you define semantics this way. In any world, S is true, not S is false. In any world, both S1 is true and S2 is true, S1 and S2 is true. And in any world, either S1 is true or S2 is true, S1 or S2 is true, and so on. The obvious things that you have as semantics for these operations. Given these set of rules, I should be able to compute for any world where I know P, Q, R, J, M, K, W, T. Right? Those are the only things that I need. So P, Q, R, J, M, K, W, T. Okay? This sentence is made up of only those guys. Right? That actually, how many are there? 1, 2, 3, 4, 5, 6, 7, 8. So there really are only 2 power 8 words in which this sentence, the minimum 2 power 8 words in which this sentence can be evaluated. Right? And in any one of those words, so for example, let's say this is true, this is false, this is true, this is true, this is false, this is true, this is false, this is false. You should be able to plug these guys in and say this entire sentence is either true or false. There is no in between. Right? That's basically what you mean by the meaning of the sentence in a given word. Okay? And so I will be able to, this is basically, by the way, the fact that the truth of a large sentence is computed in terms of the truth of its constituents, it makes this truth functional. And propositional logic, all deterministic logics have this beautiful property. That's why they're easy logics. Probabilistic logic doesn't have this property. That's why it drives people up the wall. You know how many times we make, most of the mistakes we do in reasoning in our real life are all connected to probabilistic logic. Because we tend to think to the extent possible in normal logic, which is the deterministic logic, and our intuitions suck as far as probabilities are concerned. If you say paradox, typically it will be a probabilistic logic paradox. Because we just don't know how to reason with them correctly. There are machines that can do it. We can write algorithms that will do it right. But our intuitions suck. For example, go back and look up Simpson's paradox, which is a very interesting paradox that comes from, basically our inability to put together statements that are probabilistically true correctly, intuitively speaking. It's not a paradox in the sense that there's some math goes wrong. It's a paradox because people think, how can it be? Okay? And typically logical paradoxes, for normal logic, it's not that likely to have a paradox because truth functionality is much more intuitive. That's the way we think. Okay? Keep that in mind. Okay, finally inference. Okay? So what I'm going to do now is, I know, so here is a situation, my knowledge base contains ARC, one sentence called ARC, another sentence called B are not C. So that means my knowledge base is the conjunction. If my knowledge base has two sentences, that means it is the conjunction of those two sentences, because they're both in the knowledge base. Okay? Given these, is it true that ARB is also, if I know these, can I be sure that ARB is definitely true?
No.
Do you understand what I'm saying? This question is similar to A and B is true, is A true? That you knew quite quickly. Well, if A and B is true, of course A is true. But this is exactly the same way, but you can't quickly compute this. That's why you need some sort of a mechanical way of computing the inference. So that's what we'll do in three different ways. First, we just compute the truth table and directly use the definition. That is, you look at the sets of words where the knowledge base is true and make sure in each of those words, alpha is also true. If so, it is a date. That's the first type. The second type, I take alpha, put a big negation, add it to the knowledge base. Then I compute this big sentence's truth value in each of the words. If it is false everywhere, then it must have been the case that alpha must have been entailed. The third is the proof theoretic inference, such as using modus ponens, modus tollens. Do people get what I just said? So that's what I'm going to do. Okay. So this one, the first type. Again, I'll go quickly. You should be able